happy to introduce Christopher Kit Biggs. He is a convener of the Brisbane Internet of Things interest group and has presented at conferences and user groups around Australia and internationally. Kit operates a boutique incubator, makerspace, and an IoT consultancy in Brisbane, Australia. Today he is presenting Open Source Voice Interfaces in 2025. Round of applause.
Thank you for that. Welcome, friends, sanguine and synthetic. My name is Kit. My pronouns are they, them. I come from Queensland and I'm here to help. I make a wildly erratic living by helping other organisations get to grip with potential and pitfall of the Internet of Things. There will be no I am not a robot checkbox to access this presentation. When I pitched this talk, it was something of an afterthought to some other proposals that I made, but I figured why not, because it would be simple to update the presentation that I gave in Gladstone last year to cover what's new since then in the interim. Well, if you missed my presentation from last year, you're in luck, because almost all of what I said then is now hilariously out of date. I often repeat that artificial intelligence is doomed to failure. If it doesn't work, we have nothing. If it does work, we have less than nothing, because we have a whole argument about where to draw the line between software and slavery. When I first gave this talk, it was a disclaimer that I wasn't going to spout off about AI. I didn't manage it then, and I'm not going to manage it today. A year ago, a number of people were claiming that we soon will, or perhaps already do, share the planet with artificial general intelligences that are smarter than humans. I found that amusing because the only person I personally knew who used the term AGI was a raving charlatan, and how would I be able to tell the difference between that person and all these other luminaries? I figured it out now. AI blew past the peak of inflated expectations, and here we are in the trough of disillusionment. The charlatans have cashed out already. If you're still at the table, consider that you might be the designated sucker. I'm pleased to say I set that whole schmozzle out. Now, the last year has been a bit of a downward spiral on the concept of technology as magic. Household voice assistants from the big three have run out of steam. Supermarkets without checkouts have turned out to be smoke and mirrors using offshore wage slaves. The metaverse and Apple Vision sank without a trace. And large language models turned out to need a continent full of underpaid engineers to restrain their tendency to spout utter rubbish. So maybe the whole concept of conversational interfaces is over. It might never work. But I do want to check the bathwater for any trace of babies before we throw the whole thing out. So here's my evil plan. We've just reached a point where last year's phones are doing search recognition on the device rather than having to transmit everything to the cloud. And right now we can buy small form factor computers and even microcontrollers that have the AI acceleration hardware that we thought we were going to need to do conversational interfaces, at least able to do voice recognition on the device without needing any cloud services. So finally we have the potential to roll our own conversational interfaces without the cost, latency, and creep factor of those cloud services. So what I want to do next is go through all the components of a conversational user interface and see where the state of the art stands. Okay, so in order to understand how to do all this stuff, we're going to have to break it up into steps. And that makes total sense for us in the open source world, because many of these steps resolved to single software projects, in many cases maintained by a single person. And in most cases, there's a number of competing products that you can choose from to perform each step. And sometimes all this software runs on the one system, sometimes it might be spread across a number of systems. And that's what gives us flexibility, because we can arrange the software to fit the kind of tasks we want to do. And the first thing we want to do is get some sound. This used to be hard, but then the future happened. A $5 microcontroller is today fast enough to just run analog to digital conversion on the output of a microphone and process the audio in real time. But don't do that. Digital microphones are cheaper than chips, and it's especially worthwhile getting a multiple microphone array or other hardware that can do some of the work of isolating background noise and echo and tell you whether or not you've got good signal. And Bluetooth earbuds are now dirt cheap, and software to talk to these is now built into your embedded operating system, so you've got another cheap and easy way to acquire your audio there. The next thing to care about after we have some audio is whether anyone is actually speaking. Sometimes the hardware can do this for you, and if not, there are off-the-shelf open source libraries that just do that. They analyse your audio to determine if it's worth actually thinking about what the bits are. This one is a really simple library that just has one function. It tells you whether there's silence or speaking. And you can twiddle all sorts of thresholds and priorities and other stuff. But this is a lovely example of an open source component that just does one simple thing in a pluggable way that's sort of one person's worth of software infrastructure. I contrast this with the big three commercial voice interfaces where the same steps exist, but there's no options for the user about how they fit together. Speech recognition is expensive in terms of computation, and if your wearable computer needs a heatsink, this can affect your choice of which body parts you want to strap it to. So most of the time we use what's called a wake word to activate the speech recognition subsystem. And this is a privacy and efficiency trade-off to some extent. You don't want to accidentally trigger effects due to snippets of normal conversation, and in those older systems you don't want them sending all your private conversations to the cloud. So this was the first piece of the puzzle that got implemented on device. Alexa, OK Google, Hey Siri. Those are phrases that the big three default to, and the dirty secret is that those phrases were mostly chosen to be easy to recognise, 3 or 4 regular syllables ending in a vowel. But easy to recognise also means high false positives, which means they start transmitting stuff that they weren't supposed to be transmitting. There was a story in the news a few years back about a couple who were having a marital breakdown, and their screaming argument got transmitted to the cloud and turned into a text message and sent to one of their co-workers. When I started considering this subject, wake word recognisers were expensive and difficult to produce. I actually thought about getting enough volunteers together at a previous conference to record the 500 hours of people saying, hey Bob, or whatever, that would be necessary to generate a new wake word. But the cost has come down from 2 weeks of supercomputer time and 500 hours of recordings to an hour on your PC and very minimal sample input. So once the system knows that it has to start listening, it has to convert the waveform produced by humans squirting air through their meat parts into symbols, and that's what we call continuous speech recognition. And pretty much every system out there breaks this out into a separate step that we call speech to text. That is, it converts audio to ASCII. But a particular neural network model that does this only works for a particular human language. But the good news is that over the last year I'm seeing the offerings shift from English and maybe Chinese to here's a laundry list of supported languages. Now you don't strictly have to do voice recognition. The alternative is what we call word recognition. Instead of converting the speech to text and then having a separate step to understand the text, some simpler systems simply have a limited number of phrases that they're expecting to hear, and they perform the much simpler task of just saying, does this audio sample match phrase 7 or phrase 12 or none of the above? Now that's obviously less flexible, but it's also something that can be done on a very small microcontroller. And once again, the state of the art in that arena has progressed quite a lot in the last year. Last year I was working with software that could discriminate about 100 phrases, and that left me reloading my phrase book with different phrases in different contexts during the lifetime of my application. But those limits have more than doubled in the last year, which gets us past the annoying problem of having to juggle our phrase books. Now back to voice recognition. We have a phrase converted to text. Now we want to know what to do about it. That's called intent recognition, And that's the big task that the commercial voice assistants focus on. Google, Apple, Amazon, they all have complex ecosystems that direct voice commands to their various sub-products, the music players, the home automation, the apps on your phone, or the marketplace of voice services they expected vendors to create, and the vendors unfortunately did not. So I would be really wary of building into these big three voice ecosystems from now on, because those vendors have quite clearly lost interest in them and now see them as a cost rather than a revenue potential. But in the open source world, there's a handful of projects which do this for us, and I'll touch briefly on that later. But let's finish the big picture first. Processing an intent may be a fire and forget operation. If I say something like turn on the light, then that's a fire and forget, a complete conversation in itself. More complex operations like composing a message or scheduling an appointment may involve back and forth. Some systems require a conversation component to handle these complex interactions, and Apple's ecosystem is particularly good at that. And when an intent involves to an action, there has to be some communication with the outside world. A message might go to a light switch, or to an app on your phone, or it might go into a message processing system where a number of pieces of software act upon it. And the last piece of the puzzle is feedback. Answering, okay, yes, I opened the pod bay doors, or I'm sorry, Dave, I can't do that. And in this part of the puzzle, we've had on-device speech generation systems since the 1980s. They weren't great, but it was feasible. In fact, speech synthesis is such a solved problem that I'm getting sick to death of hearing AI voices. We're not just at the top of the uncanny valley. I'd rather have an obviously imperfect voice generated on device than be hearing the same 4 AI voices every time I open YouTube. Okay, so now we're ready to start looking at some actual software products that you can run on a small Linux device or similar. I'm going to go bottom up, that is, I'm going to talk about the low-level operations that deal with audio input or output, and then we'll consider the intent and conversation handling later. So let's start with wake words. I'm not even going to waste your time with anything that hands audio off to the cloud here. All this stuff will run on a Linux box or other open source operating system. And the field has shaken out quite a lot over the last 2 years, so I think there's only about 2 systems that are worth mentioning. Pico Voice is a very portable system that runs on a bunch of processors. It supports something like 16 languages. Their open source library is called Porcupine. It's up on GitHub. I think it's non-commercial use only. They request a license fee for commercial use. And if you want to train your own wake word, they have a website which will walk you through that process. Also works with a bunch of human languages and programming languages, but their training engine is not open source, so that might affect your decision to use it, or you might want to applaud them for actually having a business model. Now, the new kid on the block is Open Wake Word. I was quite excited about this last year, and even if you don't end up using it, its documentation has a great explanation of the problem space and even mentions which other projects in the arena might be better than it for a particular use case. Open Wake Word trains its models on synthetic speech, so you don't even have to record human speakers. That sounds like black magic, and I thought it was complete rubbish when I first heard it, but it does seem to work, and in fact, this software hasn't really changed much. I was looking at the changelog today. In the last year, I think it's at the point where everybody's using it, and it's good enough that it can be considered pretty much a solved problem. So that's wake words. Now the next step is speech to text. Again, there's a number of cloud systems that I'm not even going to talk about. The offline speech recognition engine that was leading the pack last year was OpenAI Whisper. Nice, friendly license, strange, kooky company. That might sour you on having anything to do with them. Fortunately, there has been a Cambrian explosion in speech engines There's a bit of an arms race going on between NVIDIA and OpenAI, and they seem to be cranking out new models almost weekly. There's a URL up there that will give you a list of about 30 different speech-to-text models with details on their performance and various pros and cons. And the other big win is that a number of these speech engines can run on very low-end Unix computers, so Raspberry Pi and other single-board computers. And particularly we're starting to see now some of those ARM-class credit card-sized computer chips that have AI accelerators built in. Okay, so let's skip over intents and conversations and look at text-to-speech. This is another area where the bleeding edge of quality is cloud-based, but the on-device options are good enough. I'm just going to refer you to that webpage up there, which runs down again the pros and cons of a large number of offerings. But the TLDR is that if you're generating English, you've got lots of good choices. But if you want to generate speech in many languages potentially for users, then there is only a small number of projects that are what I would charitably describe as capable all-rounders. The one that stands out, at least to me, is Piper, and that's what Home Assistant, the home automation program, uses. It's got a number of voices, supports a number of languages, and it's being actively developed. The things that are new in speech synthesis this year are emotional synthesis. That is the ability to make your synthesized speech sound happy or sad or homicidal or whatever you desire. Unfortunately, you might now notice that every other YouTube video is the same AI voice shouting at you in an angry tone of voice, thanks to this improvement in technology. Now I want to turn to hardware, which is my main point of excitement. Pretty much everybody starts out with the Raspberry Pi single board computer. I have more of them lying about than I know what to do with, and so that's what I started out with too. The latest Raspberry Pi 5 has a PCI slot on it into which you can put the Google Coral AI accelerator, and that makes it quite a powerful option. But this year, I am going to withdraw my recommendation to go with Raspberry Pi. I just got this new third generation Radza Zero, the one on the left there, and that is part of my wearable computing system. I had the previous model and it died on me a week or so ago, so I just got that one in the mail on Friday. And if you spend $50 more than that, so on the order of sort of $200-300, you can get its big sibling on the right there, which has something like 6 trillion AI operations per second in its AI coprocessor. Now, my apologies to your wallets, but that's one of those Raspberry Pi lookalike boards from Radza with the 8-core CPU and the neural accelerator embedded in a project called AI in a Box. Now that little thing there on its own can do continuous speech transcription. I can run large language model chatbots on it if you think that's fun, but at about $350 it's quite a compelling appliance for voice processing. But don't click buy yet, I've got some other things to show you as well. The good thing about that Raspberry Pi playing cards form factor, or that smaller Pi Zero factor, is that you can get a number of quite good off-the-shelf microphone hats which sit on top and take care of your audio input processing. My notes actually say breathe at that point. The concept of doing audio processing on a microcontroller sounded absurd 5 years ago, but that's all changed and I'm super excited. The arrival of AI model acceleration on microcontrollers was the catalyst that got me interested in voice interfaces back in 2023, and led to this talk and the one that I gave last year. The architecture that pretty much everyone uses in that low-end microcontroller space is the Espressif ESP32 processor. You'll find that in the light bulbs and many of the Wi-Fi light switch and motor controller and such things that you can get from Bunnings or online. This CPU is sort of got 2 CPU cores, couple of 100 megahertz each, handful of megabytes of flash memory, couple of meg of RAM for about $10. So, power we would have drilled over in the 1990s, but pretty modest for today's. And for a bare bones job, all you need is an ESP32 development board and a microphone module, and the whole lot could come in under $20. There's a couple of development boards out there that combine CPU and microphone and even a screen, and these are just fine as long as you don't need to have absolute minimum size. I've done most of my work on that round one on the left there, which has got 3 microphones, a bunch of multicolour lights, and runs on battery. There's another quite pretty little board from M5 there that also has an LCD screen. Your hardware choice is really going to depend on what your application is. If you're doing home automation or conversational interfaces, then you probably want one of those big boards with lots of microphones. In that case, your ESP device is going to do the wake word processing, and then it's going to stream the audio to your conversational engine running on a Raspberry Pi or a PC or something. The other use case, and this is the one that I'm most interested in, is building direct voice into an appliance where the microcontroller is also running the whole appliance, and it just happens to also be able to do the voice processing as well as run most of the rest of whatever it is that it does. And if you think about off-the-shelf Internet of Things gadgets like light bulbs, motorized blinds, and what have you, they just take orders from your intent processor, which might be in your voice assistant base station or it might be in the cloud. But that means that they only work as part of a system. If you take them somewhere else, they stop working. But on the other hand, who takes their light bulb or their curtains out to lunch? But my interest is for tools that I can take with me, either body-worn or in a toolbox, to be able to give those devices instructions without needing to set them up with a network connection. So here are some boards that I've been playing with in the last couple of weeks. The one on the left is an ESP32S3 with a little colour display on it. The one on the right is one of the newer RISC-V chips from Espressif. And because that one on the right uses an open source instruction set architecture, which means no licensing fees paid to ARM, our gracious sponsors, bless their name, it costs as little as $2. And both of these have Bluetooth and Wi-Fi built in. But this is the gadget that everyone is talking about this summer. This is the official Home Assistant voice module. I have one here that I can show you later if you like. I got this developer preview model just in time to hop on the plane last week. So I haven't even managed to do anything with it yet, but it's both exciting and disappointing. The exciting is it's got microphones and lights and a click dial like your old iPod. It's built on that ESP32S3 microcontroller. It's fully open source, but it's not powerful enough to do speech recognition, so it shunts your voice either to Home Assistant's cloud servers or to your own Raspberry Pi. So if you're using Home Assistant for household automation, it should drop right in, and it's the obvious choice. But because it's completely open source, you can reprogram it to use it as a component in whatever voice system you like. Now, as far as I know, we don't yet have a general speech-to-text system that runs unassisted on microcontrollers, but I am hoping to be proven wrong about that this year. I didn't quite get it last year. But there's a number of options for less ambitious phrase recognition on the device. There's a couple of systems, open source systems that work with Google's TensorFlow Lite and will run on embedded ARM processors and embedded Espressifs. But on this ESP32 architecture, Espressif shipped their own voice toolkit, which is open source, that gives you wake word recognition, it gives you audio processing, echo cancellation, noise cancellation. quite flexible phrase recognition, and this is what I've been using for some of my experiments in voice-controlled appliances. It can recognise up to 300 phrases, and you can specify those either as English text or as phonetic voodoo symbols. And if it thinks it's recognised one of those phrases, it'll give you a confidence level. It'll say, I'm 92% sure you said open the pod bay door. But I found it to be very accurate. Now, I spoke about a number of projects utilising all these tools last year, and I won't repeat those, and you can find those slides on my website. But my project for this year is an assistive headset. I do a lot of work on very small electronic devices, and I have increasingly old and unreliable eyesight. So what I want is a headset that can drop down magnifying lenses or the view of an endoscope camera or deploy up some LED lights under voice control. And I've evaluated a number of off-the-shelf video monocles, and I've found all of them to be unsuitable so far. This one on the screen is called the Liligo T-Glass. It's about $60. It's got an ESP32S3 processor. It's open hardware. I would be prepared to love it to bits, but unfortunately for my spectacles, I can't get the screen to focus. If I take my glasses off, perfect. You know, I see a little black and white screen floating in space, not particularly high definition, but as soon as I bring my glasses down, it goes out of focus. So, of course, I'm building my own now, combination monocle and voice processor appliance, using that S3 with the colour screen and some lenses that are intended to go into VR headsets. Now, these things I'm super excited about. These things are called the Even Realities G1. They cost about $500. They support prescription lenses, so you can get your own lenses put in them. They have a micro LED projector in the frame. No camera, thank goodness. You know, it's so much of the history of head-worn displays has been sidetracked by the what I call the squick factor of the fact that they have a camera in them. But these ones just have what's called a micro LED projector in the arm, and they have a little bit of circuitry sits up behind your ears. So they're essentially indistinguishable from ordinary spectacles, and they can project monochrome text into your field of view. There's an even cooler product that is quite similar that just been announced a couple of weeks ago. Unfortunately, I lost my link to the press release, but I think it's going to be up on Kickstarter later this year. So there is so much more I wanted to tell you. It's going to be a super exciting year, presuming the world doesn't end. Today we've looked at a whirlwind tour of the architecture of voice interfaces, two broad approaches of using a single board ARM computer and a microcontroller. We've touched on some very shiny products coming down the pipeline for home automation, and I've shown you some of my plans for this year's Vanity project. I do hope you found some of that useful, and I do have samples of some of these devices with me. I'm happy to do a bit of show and tell or take any questions you have about the talk and the problem space. Thank you for coming, and if you're looking for advice in the IoT space, I'm here to help. Thank you.
All right, guys, you know the way we go. Hands up for any questions. No? Going to swarm them all afterwards? Aha.
G'day, Kit. Blue sky question for you. If you could design the hardware for your home assistant so that it had really fast speech recognition, it had really responsive wake word detection, voice activity detection, what would you like to build?
Do you mean what hardware would I choose, or?
Let's say you were the head of Home Assistant. How would you build it?
The people that made the one that I bought last week make a thing called the Radsa 5C, which is the size of a Raspberry Pi, but with an 8-core processor, 32 gig of RAM, and a 6 tops NPU. So that's pretty much everything you would want in terms of hardware capability. And we're talking somewhere in the order of $200 to $300 for a device like that. It's the situation right now with Raspberry Pis and things that look like Raspberry Pis is very much like it used to be back in the days of the peak of popularity of the iPod. You go into the store and you look at the one you think you wanted, but then for $50 more there's one that's twice as good, and for $50 more than that there's one that's 2 more times as good, and next thing you know you've spent $600. But yeah, no, it's an exciting time to be a hardware nerd.
I thank you. My wallet does not.
Okay, anybody else? No, in which case, one last round of applause, and thank you.